Hello everyone, today we'll talk about the solution to the problem divide nodes into the maximum number of groups. This is essentially a graph coloring problem, so we'll get into the details of the coloring later on in the video as we are solving the problem. It's classified as hard. It's again one of those hard problems where the idea is not maybe super hard, but there is something to be done on the implementation side, and in general it's a bit more workload than a typical medium problem, so I guess it deserves the hard rating. Since the coloring that we want to do is specifically not only the neighboring nodes have to be colored in different colors, but they have to be colored with colors that are numbered consecutively, which essentially means that when we take a node that has the smallest possible color, then all its neighbors have to have the color that's one bigger than it. So we immediately know which color their neighbors have. And so on and so on, right? So because this is what this means, and one node has to have the smallest color. And notice that since that node gives us the color of its neighbors and those neighbors of their neighbors and so on, we essentially have some of those colors predetermined, assuming that we select this node. We are also here given the fact that the given graph may be disconnected, which is nice that they give this explicitly. In general, you should always make sure when somebody's describing a problem to check if the graph is connected or not. Often when the graph is disconnected, as in this case, this will just be some independent problems that are easy to join together. And indeed, in this case, when we have this number of colors, then we can color every connected component separately with completely unique set of colors and just add those numbers of colors together at the end, right? So, for instance, we can start with small numbers on one component and then million in another component and 2 million in another component and so on. So they are completely independent in that way. So, okay, for every component we have separate independent problems. When we select the node that has the smallest color, it determines all the colors of its neighbors, and so that means that it determines the colors of the whole connected component. So maybe we can just try for every node within a component to select it as the smallest number, propagate all the colors, select the best assignment out of all of those starting positions as the maximum number of groups, and sum them together over all the connected components. And indeed, this is a solution, and this is a solution that I'll present to you now. So really just two pretty simple observations, and then you just implement it, which is a bit brute forcey, but it's enough for this problem. So how do we find because maybe it's possible to not find those connected components explicitly, but I'll be finding the connected components explicitly, and the process for both finding the connected components and for calculating or for propagating colors is very similar. Propagating colors has to be done using a BFS. That's because that propagation, assuming that the first node has color, let's say 0, then that propagation will just be the distance for every node from that starting node. So that's a very trivial, very standard BFS. And we can also find connected components using a BFS or a DFS, however we like. And we find a component to then iterate over the whole component, trying to start from that position and taking the maximum over all of those positions. So that's the reason why we find it explicitly, to be able to take the maximum over a component, but add together the maxima over all the different components. Okay, let's jump into the code finally. One last thing. Return -1 if it's impossible to group the nodes with the given conditions. Can it be impossible? Of course it can be impossible, since we are coloring with consecutive colors. Then in particular, when we look at the parity of the nodes, then always a node with an even color will have all its neighbors have an odd color, because they differ by exactly 1. Which means that any correct coloring will also give us, for free, a 2 coloring of the graph into odd and even groups. And not all graphs can be colored with 2 different colors. Only bipartite graphs can be colored with 2 different colors. So that's the definition of a bipartite graph. That you have 2 parts, and there are no edges within any single part. All the edges are across parts. But it's easy to see if a graph is bipartite or not, and I'll mention it when we get to it in the code. We don't have to check it explicitly in a completely separate portion of the code. So we are given a list of edges, so we create a graph. Nothing special happening here. And we'll be maintaining, of course, a set of visited vertices, and also the result. So the result will be sum over maxima for every connected component. And we go over all the vertices. If the vertex was visited, we continue, otherwise we visit it. The first step for visitation is to find the component, so we start with V, and now we go through everything in the component, look at all its neighbors. If they are visited, do nothing, otherwise add them to the visited set and add them to the component. This is Python, so we can iterate over a list while appending to it, so this is a very nice short way of writing it. And now here we have this connected component, and we've marked all the nodes as visited, but we still have to try to set them as the minimal group within their component. So let's do it now. So we'll be taking the maximum over all the possibilities, so best is 0, and we try to start at any node in the component. We need a new set of visited nodes. In this case, we'll also keep track of the layer of the group that the given node has for the purpose of checking if the graph is bipartite. And now we do a BFS. So here we had a list for a DFS. Here we have a queue or a deck in Python. Because we want to be a BFS, we want to put into the right end and take from the left end. And now here we have the number of layers, standard BFS, so we remember the current size, iterate over the current size, and after every this big iteration of over the current layer, we increment the layer number. And now we take the node, we look at all the neighbors, we check if the neighbor was visited, if so we continue. However, and here is the bipartiteness check, what we have to do is we have to check if there is an odd length cycle, because that's the definition of a graph that's not bipartite. A graph where there exists a cycle, and that cycle has an odd length. It's easy to see why it precludes a graph from being too colorable, because we start with color 1, then color 2, color 1, color 2, and we reach back to the original node with a different color than we started. So every cycle has to be even. And one way of checking if a cycle is odd, if there is an odd cycle, is to just do a BFS, and the situation we'll get is that we'll be trying to visit a node that has exactly the same layer as our current node. And in that case, because of course we won't be really trying to visit a node that's, because this is a BFS, so we are visiting the node the earliest that it's possible to visit it. So we'll be visiting two different nodes at the same time, so at the same layer, and they are connected to each other because now we are trying to visit one from the other, which means that we have reached the end of that odd length cycle, and this is the clash where we cannot give them two different colors. So if the color of the neighbor is the same as our color, we return -1. And instead, if everything is okay, we give it our color +1, append it to the queue. That's it. For every layer, we increment the number of layers. And now, if we haven't returned -1, and notice here that this return -1 is just the return from the whole function, from the whole solution. If there is at least one case in which we have an odd length cycle, the whole problem is impossible to solve. And we have to return -1 as the general answer. We remember the best answer, again, over all the starts in this component. After processing the whole component, we add it to res, and at the end we return the res, so this is the sum over maxima of all components of the maximum number of layers that we can separate the component into, and we find it by just trying every possible starting vertex as the vertex with the lowest value for its group, for the lowest number of its group.